uh, and uh, so my goal today is to tell you about some problems that I'm interested in algebraic dynamics, a uh, fairly new subject in dynamics. And my plan is to start with the following. I will tell you about my problem. So um, about what has been known and what has been done, uh, and then I will go deep into how one can understand this problem. And my main point is to talk about B divisors, not B divisors, but B divisors will be like the object I will look at, but the but what I will do is try to endow B divisors with certain topologies, like in functional analysis, to do to understand my degree growth problem. Okay, so my point is to try to link out these two themes in this talk. So let me start with the setup. So I will take X, the complex projective space of dimension D. If you want something more complicated, you can ask for a generally a smooth projective variety defined over C. And if you want even better, you want, okay, define over an algebraically closed field. Uh, and you have to ask that, yeah, countable. Now you can um, fix an ample divisor on X. And my dynamical systems are given by rational maps, so dominant rational maps. So they are given in coordinates by, if you take x0, xd, some homogeneous coordinate, and you fix p0, pd, some homogeneous polynomial of the same degree with no common factor, and then you look at the induced map. So this gives you, for certain points, you can calculate P0, PD, and this gives you a map. Of course, it has problems because you have indeterminacy points. You have the locus where all the polynomials vanishes at the same time. And this, because of this locus, there are points where your map is not defined, okay? Nevertheless, I can define the quantity that I'm interested in, just the algebraic degree of my maps. Well, it's the common degree of my homogeneous polynomials. Okay, and now I can tell you my main focus is the sequence degree of this. I want to study the growth of the sequence. N gives degree of algebraic degree of Fn, where Fn is the nth composition of F. Okay. Okay, so so that's my problem. And for the sake of my talk, I will need something quite a little bit more general than just the algebraic degree. And my algebraic degree, I can interpret it as the following. I take a hyperplane in the target in X, and then I take its preimage by F. It gives me a hypersurface of a certain degree, and then I intersect it with D minus 1 hyperplane and I count the number of points. So geometrically, this can be done for every codimension hypersurface subvarieties. So if I have a subvariety of codimension K, let me take, for example, an intersection of hyperplanes of codimension of K hyperplanes. I can take their preimage and then intersect it with D minus K generic hyperplanes H D. So this is k plus 1. And this, using this, so you get something of a certain degree, and then you intersect with enough hyperplanes, and you count the number of points. And this, you can calculate this number using like an intersection theoretic formula, and it is given by the following. So take gamma tilde, the desingularization of the graph of f in x times x. And so you have a birational map from gamma tilde to pi 1 to x, and pi 2, this is a generically finite map. And this intersection here can be interpreted as the intersection product of, so you take your ample class at the power k, so this corresponds to the intersection of k hyperplanes, and then you pull back by this map, so you end up here, and you push it down here, you get a class here, and then you intersect with d minus k hyperplane, so I intersect it with omega at the power d minus k. So this is to say that, well, the calculation that you're doing here is purely cohomological. I can only take, and it depends only on the choice of k, which is a certain codimension. So for the algebraic degree, I took codimension 1. So right now, so you can ask the same question: what is the growth of degree k of fn when n grows to infinity? And the first result that we know is due to Russakovsky-Schiffman in 1997. And it tells you that the k degree of fn grows at most like exponential plus epsilon at the power n. So, and this exponential factor is lambda k. Okay, so roughly should look like an exponential. So at most lambda k plus epsilon at the power n. Okay, and so this is because this degree sequence is submultiplicative, and this submultiplicative allows you to define this ratio. Any questions? Okay, then I will go to the next things. So this case dynamical degree is an important number because it is actually a birational invariant. So if I took not f, but a conjugate of f by a birational map, and I compute lambda k, then it's the same number. And it is important, for example, if you have an automorphism, then there's a result due to Gromov-Yondin that says that if you take the max of the log of lambda k, it calculates the entropy, the topological entropy of your map. And so for that, those are like I understand them as important invariants of my map. They measure the complexity in codimension k for each k of my map. So let me go to how I can understand this question. So I told you now I can calculate the algebraic degree in a complicated way using intersection product of cohomology classes. So let's do it in let me tell you more about it. So you can do it as follows. So you take the Néron-Severi group of X. So here I understand it as the H11 intersected with H2 of XR, and but in a more formal way for me, I want to think of them as cycles. So it's the group of divisor cycles modulo this numerical equivalence. So numerical equivalence is, I say that two divisors are equal if and only if whenever I intersect with any algebraic curve, I get the same number. And so I I look at this group of divisor modulo this equivalence, and it is what I'm interested in. It's the space of classes that I will work with. More generally, you can do it with codimension K classes with using the same type of formula. So instead of taking a divisor classes, you take cycles of codimension K, and then you mod out by the numerical equivalence. And the main observation that I want to stress today is that, okay, my question is very straightforward when F is very regular. When F is regular, I have a pullback in this endomorphism space of NK. Okay, and because I can kind of pull back codimension K classes, and it passes to numerical equivalence. And the main point is that, okay, you have this endomorphism of NK, but these invariants that I told you, lambda K of F, the dynamical degrees, they are the spectral radius of those operators acting on each NK. Okay, so this is I denote it like spectral radius like this. Maybe it is yeah. So this is so I call it the spectral norm inequality equality. Even better, because F is an endomorphism of finite dimensional vector space. You know that the degree of F, basically, this is controlled by taking your ample class at the power K, taking its preimage by Fn. And you know that there is at worst a Jordan block. So in fact, the degree K of Fn is controlled at worst by an exponential factor, and at best by a polynomial factor times an exponential factor. So this is lambda K at the power n here. So, okay. And so this is the size of your Jordan block, basically. So this is the case where F is regular. And let me tell you now, once you see this, you can say, okay, I understand very well what happens in the regular case. So let us think that it should be the same for arbitrary rational maps. So this is what I call a folklore, how do I say, folklore conjectures. There have been many cases where we know it's true, but the general case so far has not been proved yet. So you want to say that, well, this polynomial degree growth at works is what happens in general. And so let me tell you when this is, so this is one of the questions that I'm asking. The second question that I'm asking is whether, okay, lambda K, lambda 1, let's say the first dynamical degree, is an algebraic integer. Okay, this in finite, in the regular case, it was a spectral radius of a finite matrix. So it should be the case in the general setting, right? Okay, so here are a few cases where these questions were solved. So when F is a polynomial automorphism of C2, then you know that lambda 1 of F is better than algebraic. It's an integer, and this conjecture holds. And for birational maps of P2, so or arbitrary surface you have that lambda 1 of F is an algebraic integer, and this conjecture also holds. So these are two results in dimension 2, so on surfaces. So let's see what one knows. Let's try to go to non-invertible maps. So when you start with a polynomial map from C2 to C2, so not an automorphism, then lambda 1 of F is also an algebraic number, and this conjecture also holds. So this is fairly recent, recent results. But if you jump 10 years after, there's a counter example that says that you have a rational surface map F, so not birational, such that lambda 1 of f is transcendental. So our, how do I say, our intuition with finite regular maps is kind of false. So this is uh, um, yeah, very recent, and it was one of the new subtleties in our field. Another result done about surface maps. So if you take a x surface and you suppose that the first dynamical degree square is strictly bigger than the second dynamical degree, then there exists a constant. Then you know that the degree growth here is growing exponentially fast, and with the right factor, so purely exponentially. And so let me tell you this a little bit about this condition. So this condition is actually a consequence of the log concavity of certain intersections. So when I define the degree, the degree 1 of f was given by taking fn of fn was by taking fn of omega times omega to the power d minus 1. And the log concavity Chovansky-Tessier inequalities tell you that this square is bigger than the intersection of fn of omega square times omega d minus 2. And so when you take the asymptotic limit of this tells you that lambda 1 square is bigger than lambda 2. Okay, and bigger or equal. But if you assume a strict log concavity, so not equal but strict, then you have this phenomenon. Okay, and my goal today is actually to tell you that this result will hold in any dimension. Okay, so that's the goal of my talk. But so let me go to what happens, what people knew in dimension 3 and on. So in dimension 3 and on, here are the only cases where we can have where people have verified conjecture A, or are some weaker version of them. Okay, so you have the regular case. Okay, so we already talked about it. You have the case where your map is monomial, so you only allow monomials in your in the map defining your in the terms defining your map. And so this is a toric geometry. You can use toric geometry to understand this question. And so this lambda k is always algebraic, and this conjecture still holds. And you have the case of Blanc-Santon, where they study like automorphism, but of algebraic degree smaller or equal to 3. So they calculated all the dynamicals degree, and this result is also quite difficult. Then there are some cases where people have bounded like the degree growth, not calculated the degree growth explicitly, but bounded it. So a lower bound in certain cases, and certain people have studied the slow degree growth. So when it grows slowly, it cannot go too slow, but it cannot go, it is always growing faster than a linear map. Yeah, and so those are, but you have to always somehow, people knew how to understand those questions by putting more rigidities on the maps. Okay, and so so the goal of my talk is to tell you about this this result with Charles Favre. So you assume now that X is smooth projective of dimension D bigger or equal to 2. You take a dominant map and you assume this strict log concavity. Then you have a constant such that the degree grows purely exponentially in constant lambda 1 of f at the power f. And let me tell you one of the consequences of this result. The second thing is that we can apply our techniques and to verify one more case of conjecture A. So if you take a polynomial automorphism of C3, so polynomial map, but that is whose inverse is polynomial in C3, then both lambda 1 of f and lambda 2 of f, which is lambda 1 of f inverse, are algebraic numbers. Okay, and but for the sake of my talk, I will only focus on this part of the slide. Any questions so far?
So what is the field of definition of theorem A?
I need characteristic 0, algebraically closed, and countable.
So like for C, a priori it works only for x defined over Q bar, but not for C, for instance.
No, yeah. A priori, yeah. So basically, what we wrote, we think it should work for C, but there are some technical issues that rely on countability that we did not do in this paper.
Thank you.
So the trick is you take F, you look at the coefficients defining F, and you look at the field that contains those coefficients, and so then it becomes countable, and then you start doing it. You start blowing up accordingly to have this.
Thank you.
Okay, so you will see why it is. I will need comfortably there. Okay, so let me tell you this how I understand this condition lambda 1 square strictly bigger than lambda 2. So there's a way to understand this in a particular case. So assume you have X and abelian variety, and you have an endomorphism. Then you write the eigenvalues in the decreasing order in modulus. Then lambda 1 square is exactly the modulus of rho 1 square, and lambda 2 is rho 1 rho 2. And so the strict log concavity means that rho 1 is strictly bigger than rho 2. So basically, if I draw the spectrum of my map, I have rho 1, lambda 1 here. And then all the eigenvalues are here. And those are in the disk of radius. Those should be in the disk of radius square root of lambda 2. Okay. And so that is, and you know even better that this multiplicity, the multiplicity of the eigenvalue lambda 1 of f should be 1, okay, by this argument. And but the simplicity of the leading eigenvalue, we have an argument that is quite complicated, but that is that I want to present today. So assume that, how do you understand this simplicity? I will tell you that it is a consequence of Hodge index theorem. So assume that your map is regular, and I will tell you that the Hodge index theorem will imply that the eigenvalue lambda 1 of f is simple. So take two eigenvectors alpha and beta, and with eigenvalue lambda and mu, which is strictly bigger than the square root of lambda 2 of f. So you have the two equations, f star of alpha, f star of beta equals lambda alpha and mu beta respectively, and you do the following calculation. You multiply alpha beta times lambda mu at the power n, using the eigenvector condition. This is the same as pulling back by Fn. But the thing is that this is a codimension 2 class. So the growth is controlled by the spectral norm in N2 of X. So this is smaller than lambda 2 of F at the power N. So this tells you what? This tells you that because I have taken my eigenvalue strictly bigger than square root of lambda 2, that alpha beta equals 0, alpha square and beta square are both equal 0. So when I have eigenvectors with two big eigenvalues, their intersection and self-intersection all vanish. And so you take any surface, any generic surface in a certain way, you look at the restriction of your class to every to this generic surface, and this tells you that alpha times S and beta times S are proportional for all S. Well, the proportionality constant a priori depends on S, but actually there's an argument that tells you that this constant of proportionality is the same, so alpha, beta are proportional. Okay? So this is a very looks complicated, looks abstract argument for the proportionality, but this tells me that okay, there's only one eigenvector for the eigenvalue lambda 1 of F. Okay, any questions? Okay, so I will go to the next thing. So now my goal is to tell you how do you deal with a non-regular case. So with with a rational map, so that has a priori indeterminacies. So the trick is due to Manin, and he says, okay, you have indeterminacy sets. So every time you want to understand F, what you have to do to calculate the algebraic degree is you have to look at the desingularization of the graph of F and look at this first diagram. This is for one iterate. But if you want to iterate another time, what happens is you can lift this map F to the graph here, and you want to pull back one more time your class. So if you want to pull back one more time, you have to desingularize another time. The new graph, the new map on the lift of F. So you get another model here, and then you lift your map here, and then you get another model here up there, X3, and so on. And so every time you want to iterate, you want to pull back one time by your favorite ample class, then every time you have to do one more desingularization. Okay, and so for the nth iterate, you will have n desingularization. And so the goal is to say, okay, let us not look at this desingularization. So these blue arrows are birational maps. So let us look at not only X, the model, but look at all the families of model produced by this by iterating F. So not at the same time. And this is a space that is horrible, but you will look at what you need in this space, at the space of divisors that live in all those blowups. And so this is due, so the formalizations and the name of B divisors is due to Shokurov. And what you look at is so you have your models Xj built up from your map, and you look at the projective limit of this K classes. So it's a collection of classes that live in each spaces Nk of Xj, and with a compatibility condition. But what I'm interested in is something much more concrete, is the space of Cartier classes, and it's the inductive limit of those classes that live in each of those finite models. Basically, I am taking my ample class and I'm pulling it back by Fn to Xn. And it's a class that lives in Xn. Okay, but it lives, so this is a Cartier class. And so this space was used by Blanc-Cantat and Cantat to study the group of Cremona transformations on surfaces of P2. But we will reuse it in general to understand our problem. So how is the pullback defined in this way? Well, it is defined as follows. So if you have an element of the inductive limit, so this you have a class that lives in a model, in a finite model xj, so it lives in xj. It turns out that you have xj plus 1 is the singularization of the graph of f that maps into xj, and you have a map vj plus 1 here. And your class lives here. You can pull it back here, and it's going to give you a class in here. But in here, you understand it as an element of the inductive limit. Okay. And my goal is to, well, to take the ample class and to pull it back in this inductive limit. Okay. So far, it is a vector space. And it is with the vector space, I cannot do anything with it. So the general strategy to study this problem is to do the following. So first, we will imitate the regular case. Okay, to imitate the regular case, what we will do is we will define some norms in the space of divisors. So I need a norm in the space of divisors. I need a norm on the space of codimension 2 classes, okay? And then I need to say that my norm is compatible with my problem. So I need to verify that the map F induces a pullback action on each of those, how do I say, infinite vector spaces. And I can calculate this spectral norm, this spectral radius, and it's gonna give me lambda 1 for the first one, and lambda 2 when I look at codimension 2 classes, like in the finite case. And then you need to build an intersection theory. So you need to build an intersection theory between classes that live between 2 classes of codimension 1, and to obtain a class of codimension 2 that is compatible with your norms, with your choice of norms. So you want something bicontinuous. And if you have this, then you need also a Hodge index theorem to apply this argument that I showed you earlier in the regular case. To say that, well, the self-intersection of any 2 classes is 0 when the eigenvectors are too big. And so they should be equal, proportional to one another. Okay? And so let me tell you which norm one should choose so I am going to describe this second step, this first step. How do you feel which norm is going to be relevant, and this second one. Okay. So, and the story goes back to the theorem of Buxom, Favre, Johnson in a certain way. And so in their theorem, they proved that they created a Hilbert spaces on which they did functional analysis. So in the surface case. And their trick is to say, okay, let's reinterpret the Hodge index theorem in the following way. So you have, you take S a surface. The Hodge index theorem tells you that the neuron severity group endowed with the intersection product has signature 1 and the dimension -1. And what we're going to do is the following. So you fix an ample classes, and any class alpha can be decompose in the positive part and in the negative part. So this lives here, and here this term lives in the negative part of the intersection product. Well, what becomes negative to you reverse the sign here, you put a minus here to have an Euclidean norm, to get an Euclidean norm. Okay, so if you do that, you get an Euclidean norm, and you see this formula can be written can be extended to the inductive limit of all compactifications of S. So this is the norm that they defined, and they found this so that is what they used. Okay, and what we will do is do the same in higher dimension, but we have to say, okay, remember that in our Hodge index argument, we needed a restriction argument to restrict to generic surfaces to do our argument. So if there is this restriction argument that happens, well, let's try to make it work directly by defining a good norm for which the restriction has to appear. So you start with a class alpha, and what you're doing is like you say, okay, you restrict your norm, your alpha to any generic surface. And if you have you restrict your class to a generic surface, then you can calculate the Buxbaum-Favre and Johnson L2 norm. Okay, and the conditions for your surfaces to be generic is a technical condition called the base point free surfaces. And basically, base point free surfaces is a notion invented by Fulger and Lehmann for surfaces that have that kind of avoid the bad locus. You can always choose a good representative in the numerical class that avoids anything you want, anything that intersects anything they want in a proper way. And more generally, I understand it as, you know, the right generalization of complete intersection. Okay, and in dimension 3, it is it is exactly the space of Neff divisors if I'm in dimension 3. But in higher dimension, you have to understand it as like complete intersections. Any questions?
Is the soup always finite?
Yes. So I have this normalization condition to make it finite. So yeah. So I
Is it easy to see norm balance space norm? So that means A plus B norm is less than A norm plus B norm. Easy to see that?
Yeah, in a way, if you have so if you believe this, if you have checked that this is an L2 norm, so to see that, so basically this is an L2 spaces. Here, this norm is like a Euclidean spaces in every finite level. So so it's easy to see that the norm of alpha plus beta is smaller than the norm of alpha plus the norm of beta. So it's an L2 norm. Yeah, and the hard part is to so once you have this norm, you have to take the completion of the space of Cartier classes with respect to this norm, and work with it. Yeah. And okay, the one important fact also to check that it is actually a norm is the definite positive part. So you have to check that, and this is why I took base point free here. One of the important part of base point free classes is that they generate the whole space of classes. So if you took something too small, and in all the compactifications exchange. So yeah, I mean that's the part that is somehow delicate. Any other questions? Okay, so let me go to the next. So to the next thing. So now once I want to now I want to tell you, so you have this norm for divisors, well, B divisors. And now I want to define the norm for classes of codimension 2 in this inductive limit. So what do you do? Well, the observation is that, okay, you need to make the whole machine work. So if you have S, a base point free surface, so like I mentioned before, what you can do is remark the following, that the intersection of alpha times beta times S is the same as if I restricted alpha to S times beta to S. And so if I had, so Buxom, Favre, and Johnson proved that this intersection product in L2 of S is bicontinuous. So this left-hand side allows me to say, okay, if I put the right definition, I will use this bicontinuity argument by Buxom, Favre, and Johnson. So if you have a codimension 2 classes, what you're going to define for the norm in codimension 2 is to take the soup over base point free surfaces in Xj with the normalization condition, and you take the intersection of alpha times S. So it is exactly this term here. And now we have made sure that all these restriction arguments that we did are going to be built in the machine for the Hodge index theorem. Actually, we are making sure that the Hodge index theorem will be stated in a certain way by putting everything in the definition. Okay. And so that's our norm in codimension for codimension 2 classes. And the next step is, well, to look at the completion for all these norms. And here's our application to dynamics. So you have the norms, you build the intersection product, prove that it's bicontinuous, and then you do dynamics. So you check that, well, the spectral norm, the spectral radius of this F pullback is well defined, and it's lambda 1 of F. And when you have this strict log concavity property, what happens is that this space, so this was the completion of the norm in codimension 1, the Banach space in codimension 1, can be decomposed into 2 parts. The eigenvector for the eigenvalue lambda 1, and a part E, where the spectral radius is strictly smaller than square root of lambda 2 of F. And in particular, this tells you that if you start with the class omega, well, you start pulling it back inside here, then it's going to converge very fast to this class theta plus. And the remainder here is going to be a term controlled in here. So overall, this tells you that the degree of Fn grows like constant lambda to the power n plus a term that is like very small compared to lambda 1 of F to the power n. So this is our application to dynamics. Any questions? Okay, then I'm gonna go to the next thing. So I want to go back a little bit to what to talk back about functional analysis, something to relate to what we prove. So actually, what we prove is that, well, when you have this condition on the dynamical degree, lambda1 square strictly bigger than lambda2, then what you can do is you can look at the resolvent of the pullback. And the resolvent, well, it's given by this formula. So it's like a formal power series with coefficients in the space of bounded operators of your Banach space. So N1x. And what we prove is that this analytic function has a meromorphic pole at z equals lambda1 of n. And this meromorphic pole is of order 1. Okay, and I want to state a stronger version of this conjecture A. I want to say that, okay, this is should be even better, that this function is always meromorphic at z equals lambda1. And so well, so far we don't know anything about this conjecture, but I hope it is true. And yeah, and I think this. I'm done with talk.
Much for the talk. So, any questions?
Is your formalism or your construction is a functorial? To me, the construction, the norm space, that kind of thing, depends a lot of. We do have a lot of gauge and freedom. So to me, they are really not very canonical. Are they functorial?
What do you mean functorial?
In the sense of a category. So that means we have a map morphism and the norm is canonic, is functorial. Then we could pull back or push forward, like kind of abstract nonsense.
Yeah. So what happens is when you do inductive limits, then you can pull back and it's like embedded in the machine, right? Because it's a inductive limit, so you can always go up, okay? And push forward, it's for the projective limit. So you can always push forward in the projective limit. So this is only an argument of vector spaces, okay? This is true whenever you have something, you deal with vector spaces. The hard part is analysis in here, because even though you have those operations, nothing to have more precise informations on it, then you start by endowing your space with norms. So most of norms that you will put, usually it's not going to be difficult to verify like that lambda1 or lambda2 is the spectral radius of your operators, whatever they come. What is going to be hard is to show, for example, the existence of a fixed point, the existence of an eigenvalue and an eigenvector. So for the existence, for example, you have to show that, well, you have your fn of omega divided by degree of fn. You have to show that it converges, basically. And to show that it converges, you need compactness. So you need to show that there's a compactness property. And so this is not categorical. I mean, I know too little about it, but it seems to me that it is not a canonical, categorical argument.
Okay, thank you. So, any other questions?
So I have a question. When the lambda1 square equal to lambda2, so what's happened?
So that's the interesting case. So we expect some Jordan block. So if you remember, there was this in this conjecture, you know, this 4-clock conjecture. We had this. Okay. So the case lambda1 square strictly bigger than lambda2, you fall into this part. Okay.
Yeah.
And
Okay.
when you weaken it, I expect that, okay, maybe you can get something like this, but not. So that's what people are guessing that should be true. Yeah, that you should have some Jordan, yeah, some polynomial part that appear.
Yeah.
So I hope we can control this polynomial. So what is difficult to see is how do you see a Jordan block? Well, first, how do you see meromorphy in a sense of the resolvent, and how do you see that the pole maybe of infinite order? So how do you see this? And so if you have something, sorry, it might be a pole of infinite order, so it could not be meromorphic, but if so, you have to find a way to build up like a Jordan block. So
Yeah.
most of the cases we know there's a Jordan block somewhere, but in general we don't know how to show this.
Okay. Thanks.
Thank you. Any other questions?
So we know that all the possible dynamic values of dynamical degrees form a countable set, and so it means that presumably not every automorphism of your Banach space can be realized as can come from the birational maps of a project variety. So are there any are there any obvious and necessary condition for automorphism of your Banach space to be realizable as by some birational maps?
This is so there are conditions that are, for example, so I don't know all the, we don't have criterion, but there are things that should be. So for example, in this space of divisors, you have the Neff cone, and the Neff cone has to be preserved. And so so this restricts things a lot. But apart from this condition, I have never seen any backward argument like this from a operator in the Banach space to birational automorphism.
Thank you.
Okay. Any more questions? Okay, so if not, let's thank our speaker again. Yeah, thank you. Okay, so that's the end of today's talk, and so probably we'll meet again pretty soon. Yeah, please see the announcement. Thank you.